Let's look at an example problem where we're trying to determine this one is just the formula unit of a compound. It's ionic, so the formula unit is all we need for this. I know it's ionic because it's got sodium, sulfur, and oxygen in it. So this is all given to us in percents, and remember, percent composition is percent by mass, and so really this is telling me if I have a 100-gram sample, 32.38 grams of the stuff is sodium. So I'm just going to go ahead and write this as grams, 32.38 grams sodium. And the reason I'm doing that is because if I can find the mole ratio, that's the same as the atomic ratio. So I'm going to take a mass and convert it to moles, and then that's the same thing as the atomic ratio, so I'll be able to come up with the formula unit. So 32.38 grams sodium, 22.65 grams sulfur, and 44.99 grams oxygen. Now, remember, to go from grams to moles, I need to get my units to cancel. So 32.38 grams times 1 mole per, and now I have to look up the molar mass of sodium. The molar mass of sodium is 22.99 grams per mole, and so this gets me about 1.4 moles of sodium. Same process here. I'm going to take 22.65 grams of sulfur times 1 mole per 32.06 grams of sulfur. That's moles. And this gets me about 0.7 moles. And then finally oxygen, 44.99 times 1 mole per 16 grams. And this gets me 2.8 moles of oxygen. Now, these are not whole numbers. Remember, a formula unit shows the smallest whole number ratio. But what we're going to do is we're going to pick the smallest number here, and we're going to divide everything by that. So 0.7 divided by 0.7 is 1. 1.4 divided by 0.7 is 2. And 2.8 divided by 0.7 is 4. So what that tells me is I have 2 moles or atoms of sodium for every 1 mole or atom of sulfur for every 4 moles or atoms of oxygen. Now, if you'd have just stopped here with the 1.4, 0.7, and 2.8, then you'd have had Na 1.4, S 0.7, O 2.8. And while the ratio is correct, we do like whole numbers. That is the convention in our formula units and molecular formulas. So this becomes Na2SO4. The ratios all stay the same. And of course, we know this compound as sodium sulfate. Now, this next problem is going to be a little bit trickier because now we're going to say, okay, we have a molecule, we have hydrogen and oxygen, and we're going to use its empirical formula and its molar mass or formula mass to find its molecular formula. So we're going to start the same way. First, we need to find the atomic ratio of the two substances in the compound. So we're told 0.44 grams of hydrogen. Of course, the molar mass of hydrogen is 1 gram per mole, so we're going to multiply by 1 mole per gram, and we get 0.44 moles hydrogen. Now, oxygen, we have 6.92 grams of oxygen, and remember, its 1 mole is 16 grams, so our grams are going to cancel, and we get 0.44 moles oxygen. This is hydrogen, which means we actually have a 1-to-1 ratio. This is HO would be our chemical formula, or at least our empirical formula for this thing. But we also know that it has a molar mass of 34 grams per mole for the compound. Well, if we look at HO, that's 1 plus 16, which is 17. So this molecular formula has a molar mass of 17 grams per mole, when the real molecular formula, I guess this is our empirical formula, actually is 34 grams per mole, which tells us 34 divided by 17 is equal to 2. So the molecular formula has twice the mass of the empirical formula, which just means we have to multiply each one of these things by 2. So this becomes H2O2. And then, of course, we know that this is dihydrogen dioxide, or hydrogen peroxide. Now, the last one, similar thing, we're going to go through and we're going to find the moles of each substance. So 4.04 grams of nitrogen times 1 mole per 14 grams, and this gets me 0.2886 moles. And then for oxygen, 11.46 times 1 mole per 16 grams, and this gets me 0.71 moles. Now, same trick as before, we're going to go ahead and divide both of these things by the smallest one, and when we do that, what we get is 1 here, but we get 2.5 here. Now, that's not really close to 2 or really close to 3. It's actually close to 2.5, which tells us we have a 1 to 2.5 ratio. We don't want a ratio that includes a fraction. We want this to be whole numbers. So all we have to do is get to the closest whole number, which is 5, right? So if I multiply everything by 2, I get 2 to 5. And so this compound is actually nitrogen, 2 of those, to oxygen, 5 of those. So sometimes when you divide by that smallest term, you will end up with a fraction like 2.5 or 2.33 or 2.66, which you should recognize as halves or thirds, right? And then you can multiply to make sure you get whole number ratios. This would be dinitrogen pentaoxide. And we do need to check to see if that thing has actually got the correct molecular formula. So nitrogen is 14 times 2 plus oxygen, which is 5 times 16. So 5 times 16 is 80, and 2 times 14 is 28. We add those up, and it is 108 grams per mole. And so that tells us that N2O5 is the formula unit, and in this case it is also the molecular compound.